Hello, welcome to workshop number 11. Okay, what you're seeing on the screen at the moment is what we call a Mandelbrot set. And a Mandelbrot set has got to be one of the prettiest things ever invented in mathematics. Now, this is actually a graph of complex numbers, or more precisely, it's a graph of a function being applied to a graph of complex numbers. So what you actually have on the x-axis is you have the real component, the real value. And on the y-axis, you have the imaginary component. And what you're actually doing there is you're then applying a mathematical function to that point on that graph and seeing what happens. In this case, it's got two options. It can spin out to infinity or it can go down to 0. And the color that you see there is basically how many iterations we apply to that graph. So yeah, this is going to be one of the prettiest things in mathematics. Complex numbers in action. I actually did this once on my own computer, Commodore 64. It would take 24 hours to do a single frame. This is incredibly intensive. So anyway, so this is complex numbers in action. So what we'll do is we'll leave that going in the background. It's pretty, I like that. Where are you going to use complex numbers? Well, what is a complex number? And a complex number basically is a number which has got a real component, like 6, and then it's got an imaginary component, like J4, or J negative J4. And this component has actually been done in an extra dimension, which doesn't actually exist in the real world. Often it's called an imaginary number, but it seems. Now, most of you won't actually use this until second year. Okay, so the electrical engineers in this who are listening to this are going to be the ones that use this most often. But as engineers, you're still going to come across imaginary numbers on quite a regular basis, mainly when it's proving things. So places that you're going to see differential equations, for example, will often have solutions with an imaginary component. Now, as engineers, often we're not interested in the imaginary component because you can't physically build something in that dimension. But you can use the real component. And so you work out the imaginary number, then you take the real component and use the real component. Now, differential equations often end up with this. And differential equations are an equation that has a history. So differential equations are calculus where the result that you're looking at depends upon a previous result, which in turn depends upon a previous result and so on. It's a bit like if you're in the casino. I do not recommend casinos because you're going to lose your money eventually. But if you play roulette, it's an equal chance every single time you spin the wheel. But if you're playing, for example, blackjack has a deck, so the cards going out of there have an effect on what the next probability, what next card's going. So you can use imaginary numbers, complex numbers, and differential equations. You're also going to use them in Fourier transforms, or I think you get taught Laplace transforms in 201. And Fourier transforms, Fourier series, are one of the most useful things you're ever going to learn as an engineer when you're trying to analyze stuff. Other things that we use these on are phasors, phasors, which basically vectors that rotate around in a circle. So this is going to be things like, as I said, electronic engineering, but it could also be how mass behaves on a shaft as it's spinning around. So phasors of waves, shafts, anything with a simple harmonic motion, so things bouncing up and down on springs, anything like that. So that's going to be mechanical vibration. So if you're the mechanical engineer, you might see this in vibration analysis. And also in EM waves, which again is mainly our electrical engineers here. Now, all of these are going to can be expressed or can use complex numbers. And the main time you're going to be using complex numbers is in journal papers and things where people are trying to prove things or where you're trying to derive things. So these can turn up in weird and wonderful places. Like, I'll show you one of my favorite places of weird stuff, which may or may not use complex numbers. This is just weird. So let's talk about a NOT gate for a second. A NOT gate is a component that you use in computer science. So a NOT gate, so you have a signal goes in and a signal goes out. So if you put a 1 in, it will always give you a 0 out. If you give a 0 in, you'll always get a 1 out. So that's what a NOT gate does. It inverts the signal. So if you put a 1 in, you get a 0 out. But you also get, in quantum computing, a square root of NOT gate. And what this means is that you have your square root gate here. And if you put in a 1, you get an unknown number out, you get a random, you get a 1 and a 0 out simultaneously. If you put a 0 in, you get a 1 and a 0 out simultaneously. But the practical upshot is if you put 2 of these in a row, if you stick a 1 in, for example, you'll get a 0 out. Because what happens is this 1 and 0 is then fed into this one, and whatever comes out is exactly opposite that one. So it takes 2 of these gates to do exactly this, and you can think about this as having an imaginary component. Yeah, and that's probably going to hurt your brain. I know it hurts my brain, but so basically you need 2 of these gates to act as this one, and this is actually these are actually used. These are actually have been physically built and they are used in quantum computing. So it's a basic control gate for quantum computing. So anyway, so again, enough of this. So you will see imaginary numbers, you will see complex numbers, you'll mainly see them from next year on, unless you're electrical, you might see them this year. And okay, the environmental civil engineers might not see them so much, but pretty much everybody else is probably going to see at least 1 or 2 uses of this through the course, through their education. Okay, so let's just do another one. You've got a test coming up. This is your final test. I believe you've got 24 hours to do it, which is unusual. The best way to do a test, if you can, is be fairly relaxed. Make sure you've done all the SWOT coming up to SWOT early. So do all your SWOT early. This is general advice on doing a test, is do the easy ones first. So basically what you should do when you go in is read the test. Have a look at the questions that you're doing. Do the easy ones first. And this has actually got multiple reasons. It built up confidence. It means that you know you're guaranteed to pass if you've got all the easy ones done. And then everything after that's just gravy. And a couple of things. One thing I should really emphasize here is we want to see working, especially in the essay one. You're not going to have to show working in multi-choice questions, but you are expected to show working in the long answer or the essay part of the thing. So make sure you show working. We like working. Working gets you marks. So you'll probably only get like half the mark for getting the right answer. The rest is going to be on the working. The other thing is, even if you get the answer wrong, if you've got good working, you can still get most of the mark. You might lose half a mark for getting the answer wrong, but you still might get 2.5 marks. So in a test up here is because remember what we're doing is in math, we're teaching you skills. And skills, basically, we want to see that you can actually do the skills. Okay, we're also relying upon you being honest on this, because let's be honest, the most important thing here is that you actually know how to do these skills. And if people try and use alternative methods to get their marks up, we'll discover it. We'll discover it next year when they just can't do this stuff, because next semester you're doing 102, and 102 is going to quickly go over a lot of this stuff, and then go on. And remember, really important, next semester, people forget this. If we're in physical classes, attend the first lecture. Now, a lot of people go, oh, they don't do the important stuff. But often in the first lecture, because we're not doing anything new, but often the first lecture is the most important lecture, because that's where we make sure that you've got the basics. We make sure that you actually understand what's happening for the rest of the course. So anyway, you've got a test coming up. Good luck on that. I'll probably see you in 102 next semester. If you can, I do recommend actually physically turning up to courses for lectures, because those who tend to attend lectures seem to do better than those who just watch but not do anything. So good luck on the test, and see you next year.